Greetings, AP Chemistry students. In this video, we're going to be looking at topic 6.8 of the AP Chemistry curriculum, Enthalpy of Formation. So with enthalpy of formation, we're talking about the enthalpy change, the amount of energy, when a compound forms from its elemental substances in their standard states. So for instance, if we took some hydrogen, and what's the standard state of hydrogen? Well, hydrogen is a gas, and we reacted it with oxygen. And what's oxygen's standard state? Gas, right? When hydrogen and oxygen react with one another, they typically make water. And so I'm going to go ahead and do gaseous water here. It releases a bit of energy. So when hydrogen in its standard state and oxygen in its standard state react, they produce water. And we're going to write it in terms of 1 mole of water. So I'm going to put 1/2 here to balance this reaction. And so hydrogen, 1 mole of hydrogen reacts with 1/2 mole of oxygen to produce 1 mole of water. The energy that's produced in this reaction is called the enthalpy of formation, because it's the enthalpy change for the formation of water as a gas from its elemental elements, from its elements in their standard states. And that's what enthalpy of formation is. It's the formation of any compound, theoretically, if it could be formed from the elements in their standard states. And so if you look on this chart over here, this is a chart of some common substances and their enthalpies of formation. So if we look up waters as a gas, enthalpy of formation, it's negative 241.8 kilojoules per mole. In other words, for every mole of water that's formed in this reaction, we're going to release 241.8 kilojoules. Now again, this is if this could theoretically happen, because the likelihood of elements just forming a compound in a straight shot is very low. But you can use this information for some very useful techniques that we're going to talk about in this video. So let's look at another compound, methanol here. You'll notice methanol, it says the enthalpy of formation is negative 238.6 kilojoules per mole. So what does that mean? That means that if carbon in its standard state, and the standard state of carbon is graphite, reacts with hydrogen in its standard state as a gas, and oxygen in its standard state as a gas, then all of those, if they came together and formed methanol, CH3OH as a liquid, for 1 mole of methanol that's formed, you would release 238.6 kilojoules per mole. Now, I haven't balanced this. We have 1 carbon, we have 4 hydrogen, so I need 2 here. We have 1 oxygen, so I need 1/2 here. Notice oxygen gets halves every once in a while, and that's okay. But this would be the enthalpy of formation for this reaction if it could occur just like this. Again, we're going to look at some useful reasons that we would do this in just a second. So you might be asking, well, what about an element? What would be the enthalpy of formation for hydrogen gas? And the answer is, well, hydrogen's already in its standard state. So there's no reaction to make hydrogen in its standard state. This is how hydrogen is found in nature. So the enthalpy change for this would be enthalpy of formation for an element in its standard state is 0. That's going to be important when we talk about it in just a little bit, again, in a practice. So enthalpy of formation is just the energy required to form a compound from its component elements in their standard states. Usually we can look these up on charts very easily. So why would we use this? Well, let me show you what we're going to do with this. Let's say that we had a reaction, C6H6. This is benzene, and it's in its liquid form, and we burn it. So we oxidize it. And what would we form if we're burning this hydrocarbon? Hopefully you said carbon dioxide and water as gases. And if we balance this whole thing, I'm going to go ahead and say 6 carbons, and we have 6 hydrogens. And if we look at the oxygen, 6 times 2 is 12, plus 3 is 15. So again, I'm going to write this as halves, just because, again, that makes it a little easier for if we do that with oxygen, because now we're in terms of 1 mole of the substance we're burning. So if you look at this, if we wanted to know what the enthalpy for this reaction was, we could try to find what the enthalpy of the reaction is, look it up on the internet, find a table, charts, try to figure out what the enthalpy of this specific reaction is, but not all reactions have been studied. This particular one has, you'd find this one easily. But what happens if you want to do a reaction that hasn't been studied thoroughly and you don't know how much energy is released or absorbed in the chemical reaction? Well, enthalpies of formations can allow us to solve this problem. Let me show you what I mean. We're going to take each substance here and we're going to look at their enthalpy of formation equations. So let's look at the formation of C6H6 as an enthalpy of formation. So the elements that would form these are carbon as graphite and hydrogen as a gas. And if we balance it, we would get 3 of these and 6 carbons. So if you look, this is on the table. The enthalpy for this reaction, the enthalpy of formation, by the way, if you didn't notice, has the little 0, that means standard state, so 25 degrees Celsius and 1 atmosphere of pressure. The enthalpy of formation for C6H6 is, if we find it on here, 49.04 kilojoules per mole. We're going to do the same thing for everything in here. Now, oxygen's already in its standard state, gas, so there is no enthalpy of formation for oxygen. It's already formed. But carbon dioxide has an enthalpy of formation. If you look at carbon dioxide is right here, and carbon graphite plus oxygen gas produces carbon dioxide, and the enthalpy of formation for this substance is negative 393.5 kilojoules per mole. And then last but not least, the other substance we have here is water. So hydrogen gas reacts with oxygen gas to produce water gas. And if we balance this, we need 1/2 oxygen here. And this enthalpy of formation is, for water as a vapor, negative 241.8, and that's a 4, 241.8 kilojoules per mole. Now what I'm going to do is some fancy stuff here. We know that according to the law of conservation of energy, we can form the benzene from any set of reactions we want. And so what I'm going to do is I'm going to start flipping these reactions to show them in a way where benzene reacts with oxygen to produce carbon dioxide and water. So what I'm going to do is I'm going to flip this reaction up here. C6H6 liquid becomes 6C graphite plus 3H2 gas. What is that going to do to the enthalpy of formation? What's that going to do to the enthalpy of this reaction? Well, if we flip a reaction, what you need to know is that the enthalpy for that reaction will also flip in sign, because in one direction it's endothermic and in another direction it's exothermic. So notice now we have C6H6 on the reactant side, and here we have C6H6 on the reactant side. Notice that we have carbon dioxide on the product side, and here we have carbon dioxide on the product side. So I'm going to add to this reaction that I flipped, I'm going to add C graphite plus O2 gas becomes CO2 gas. So now if you'll notice, I have C6H6 on the left, I have CO2 on the right. Notice now I have some oxygen on the left, and there's oxygen on the left here. So we're going to add one more reaction. This reaction, water's on the right in this formation reaction. Water was on the right in this reaction up here. So H2 gas plus 1/2 O2 gas produces H2O as a gas. And I forgot to write this enthalpy. The enthalpy of formation for this reaction is negative 393.5 kilojoules per mole. And for this reaction is negative 241.8 kilojoules per mole. Notice I wrote this one as formation and this one as formation because we kept the reactions exactly the same as they were for the enthalpy of formation. This one I wrote reaction because I flipped it, so it's no longer the formation reaction, it's a new reaction, so I just wrote it as enthalpy of this reaction as written. Now let's see what we can do here. We are going to add these reactions together and try to come up with the overall reaction that we're trying to study here, which is the burning of benzene. So how many carbon dioxides are produced? Notice that there are 6 carbon dioxides produced. So what we're going to do is we're going to multiply everything here by 6 moles, because we want 6 carbon dioxides when we add these reactions together. But remember, this energy is kilojoules per mole. So if this is how much for 1 mole and we're multiplying by 6, we're going to have to multiply the energy by 6 also. We're going to do the same thing here. We have in the reaction 3 waters that need to be formed. So we are going to multiply everything by 3 moles here. Everything, energy, everything, by 3 moles to give us 3 water molecules. So watch what happens when we add all this together, when we do this. We are going to get, I'm going to put everything on the left-hand side, on the reactant side of the overall reaction. So we have C6H6 liquid plus, and again, I'm going to distribute the 6 into everything, 6 C's graphite plus 6 O2s gas plus 3 H2s gas plus 3 halves oxygens. And then on the product side, we're going to put everything on the product side, remembering to distribute the 6 and the 3. So 6 carbon graphites plus 3 H2s plus 6 CO2s plus 3 H2Os. Okay, so by adding these individual reactions, let's see what we end up with. We're going to cancel anything that reacted and was produced. In other words, it didn't do anything overall. So if you'll notice, we have 6 graphites here and 6 graphites here, so I can cancel those out. We have 3 H2s and we have 3 H2s, so I can cancel those out. Nothing else can cancel out. Everything else is unique. And so what I'm going to do is start combining things that are the same and putting what we end up with. C6H6 as a liquid, and then we have 6 oxygens plus 3 half oxygens, and that'll give us 15 half oxygens, produces 6 CO2s plus 3 H2Os. And notice that when I added the enthalpies of formations and multiplied by the number of moles I needed and flipped what I needed to flip, I ended up with the exact same reaction that I was looking for. Here's the reaction I was trying to build. I found the enthalpies of formations for those substances, flipped and multiplied as necessary, and they added up to the reaction that I was looking for to begin with. So enthalpies of formations can be a really good way of adding smaller reactions to get an overall reaction. And again, the reason we can do this is because the law of conservation of energy and also the law of conservation of mass. Now, let's see what that does to our energy. We have to add the energies also. So we're going to add all these energies, negative 49.04 kilojoules. And in essence, I multiplied all this by 1 mole because I just needed 1 mole of C6H6. So the mole is going to cancel because I multiplied 1 mole times the energy per mole, plus 6 times 300, negative 393.1 kilojoules. And again, that's 6 moles times this many kilojoules per mole, plus 3 moles times negative 241.8 kilojoules per mole. If we add all that energy up, we will get the enthalpy of the reaction. So burning the benzene to produce carbon dioxide and water, the enthalpy for that reaction is just the sum of the enthalpies of formations as we manipulated them. And when you add all that together, you'll get negative 3,133 kilojoules per, just kilojoules for the reaction. So for this reaction, you will release 3,133 kilojoules. So enthalpies of formation are really useful in trying to determine the energy in an unknown reaction by adding the enthalpies of formation for each reaction. Now, that is way too complicated to do every time. You do not have to do all of this work every single time. We're going to use what's called Hess's Law and figure out that all we did was flip the substance that was in the reactants, and then the substances that were in the products, we kept in the products. We didn't flip their enthalpies of formations. So to find the enthalpy of a reaction, we can sum up the moles, 6 moles and 3 moles, the moles of reactants times their enthalpies. Oops, sorry, products. Oh, goodness gracious. The moles of the products times the enthalpies of their enthalpies of formations. Okay. Minus, because we flipped the substances that were in the reactants, we flipped their enthalpies, and this minus is just flipping signs, minus the sum of the moles of the enthalpies of formations of reactants. And this is Hess's law, which just says we add up the enthalpies of the products and subtract the enthalpies of reactants. So without doing all of this work, we end up with the exact same answer. So watch what we're going to do. The sum, that sign just means sum, so we're going to add together the two reactants. We had two products. We had two products in this problem. We had carbon dioxide and we had water. 6 carbon dioxides and 3 waters. So that's what we're going to do. We are going to add up 6 moles of carbon dioxide's enthalpy of formation, and carbon dioxide's enthalpy of formation was negative 393.1 kilojoules per mole. To that, we're going to add water's 3 moles times its enthalpy of formation, which was negative 241.8 kilojoules per mole. And that's going to be our sum of each mole times the enthalpy of formations of each product. Then from that, we are going to subtract the moles, and for our reactants, we had 2 reactants, but oxygen has 0 enthalpy of formation because it's in its standard state. So we only have to do C6H6. There's only 1 mole of it, so 1 mole of C6H6 times its enthalpy of formation, which, if you recall, the enthalpy of formation for benzene was positive 49.04. So positive 49.04 kilojoules per mole. Some of you might be saying, but we made it negative in the previous problem. Well, that's why there's a minus sign in this equation, is the minus sign automatically flips it for you. So we just plug in exactly what it is from the table. So now if you do this, 6 times negative 393.1 plus 3 times negative 241.8 minus 1 times 49.04, you will get the exact same answer, negative 3,133 kilojoules. And that's it. So the enthalpies of formation are very useful using this equation to solve for the enthalpy of an overall reaction when you don't know the enthalpy of that reaction. We can look up the enthalpies of formations for all the reactants and products, add up the product enthalpy of formations, subtract the reactant enthalpies of formations, and get the overall enthalpy of the reaction. So very useful, very useful. I'm going to go ahead and stop here. If you have any questions about this, of course, please talk to me.